So, in the early 20th century, American chemist G.M. Lewis suggested a special way to represent the approximate structure of an atom by giving its diagram. These structures were later known as Lewis structures and are basically just diagrams showing the bonding and non-bonding electrons within a molecule. These structures are extremely helpful when we're making assumptions, when we're making guesses or approximations of certain qualities of molecules, and especially when we want to know the geometric structure or basically anything that has to do with the orientation or position of different atoms within a molecule. So, in order to choose the most reasonable structure, we must know what formal charge is. And formal charge is the charge of an atom within a molecule when all of the other atoms in that molecule have the same electronegativity. And to calculate formal charge, we must know this equation right here. And that is the formal charge is equal to the total number of valence electrons of that atom minus the quantity of the total number of bonding electrons divided by 2 plus the total number of free electrons. The reason why we divide this quantity by 2 is because the total number of bonding electrons divided by 2 is just basically the total number of electron pairs that are bonded. So how do you determine which structure is most reasonable? And so for using formal charges, we usually choose or favor one structure that has a charge, an overall charge closest to 0. That is, the charge of each individual atom in that molecule adds up to 0. And also we usually choose the structure that has negative charges on more electronegative atoms. For example, in this BF3 molecule over here, you would want to have more negative charge on fluorine as opposed to boron, because fluorine is more electronegative. And based on these rules over here, we know that the structure on the left is not favored, although it does give you 8 valence electrons on the boron atom. As using the formula over here, you can calculate the total charge. The formal charge of boron is -1, while the fluorine that is double bonded to boron has a charge of +1. This already violates this second rule over here, and that's why, even though the total overall charge adds up to 0, it is less favored, because on the structure on the right, every individual atom has a formal charge of 0, and the second rule is fulfilled. And so that's why we have, and this will bring us into some of the exceptions of the Octet Rule, which we'll discuss later on. So since we've already discussed formal charges, let us talk about another rule that helps us determine reasonable structures, reasonable Lewis structures, and that is the Octet Rule. Based on its name, the Octet Rule just means that atoms tend to lose or gain or share electrons until they are surrounded by 8 electrons, valence electrons. That's why it's called octet. And this rule is often used to, as you can see in this CO2 diagram over here, the octet rule is used to determine that this structure is favored, because, as you can see, for the carbon atom over here, there are a total of 4 electrons over here, because the oxygen atom will share 2 electrons with carbon, and there are 4 over here as shown by the 2 double bonds. A total of 2 double bonds, which gives you 8 valence electrons. Also on the oxygen atom over here, on the left and on the right, there are a total of 2 free pairs, which gives you 4 free electron pairs, and 4 bonding pairs, 2 bonding pairs, which gives you 4 bonding electrons, total of 8 valence electrons around the oxygen atom as well as the carbon atom. Therefore, this CO2 structure is favored. Most rules in chemistry always come with exceptions, and the Octet Rule is no exception. So, the reason why we have exceptions to the Octet Rule is because of the law of the formal charges. And formal charges is the reason why we have these 3 different types of exceptions. The first exception is found in molecules that contain an odd number of electrons. For example, in the nitrogen monoxide molecule, you have a total of 5 plus 6 valence electrons, which gives you 11 valence electrons. And when you're trying to fill, you can only fill the octet of one atom and giving the other atom 7 valence electrons, and that's why you won't have the octet rule will not be fulfilled, although it is the reasonable structure. Exceptions can also be found in molecules containing less than an octet of valence electrons, and not including hydrogen and helium, which only have one valence electron, and you can't really consider that. This is also called a deficient octet. It's often found in compounds containing boron and beryllium. As in the BF3 molecule we just mentioned over there in the previous slide, it has, because of the formal charges add up to 0, and that the other guideline that fluorine has a more negative charge than boron, we know that this BF3 with 3 single bonds is favored over the other one that contains a double bond, even though there are only 6 valence electrons, and that's why we have a deficient octet. The final exception to the octet rule is found in molecules that contain more than an octet of valence electrons. That is called an extended octet. It's found in molecules such as SF4, AsF6-, and as you can see in this PF5 molecule over here, you'll have 10 valence electrons because it's the phosphorus essential atom is bonded to 5 fluorine atoms, giving you a total of 5 single bonds that gives you 10 valence electrons. This is an extended octet is usually found in large molecules such as PF5, because especially in molecules that are bonded to more than 4 other atoms such as PF5, because that will force you to have 5 single bonds or more than 4 single bonds attached to the essential atom, which will give you more than 8 valence electrons. Also, it's found when surrounding atoms are larger, such as fluorine, chlorine, and oxygen. Also, when the central atom is large, such as phosphorus and sulfur and arsenic. So now, after we've discussed formal charges and octet rules, let us move on to drawing Lewis structures. First of all, let's look at how to draw single atoms. And so basically, you only need to know 2 different steps. First of all, know the symbol of the element, and that is found in the periodic table. And also know the number of valence electrons, total valence electrons represented and these will be represented as dots, with at most two dots on each side. This can also be seen from the periodic table. So some of the examples are, for beryllium, you have a total of 2 valence electrons. So to draw the structure, you will start with the beryllium atom, and then draw 2 dots to represent the 2 valence electrons. Next, the chlorine atom. It has a total of 7 valence electrons. That will give you, so for drawing the Lewis structure, you first draw the symbol Cl, and then to draw the 7 electrons, you must know that when drawing the dots around the symbol, you must fill each side with at least 1 before moving to the second one on each side. So you will first draw 1 on each side, which will be 4, and then to finish the last 3 valence electrons, you'll add second. And that's why you have a single electron over here and no empty sides. Now let's move on to the hard part. Lewis structures of bonding electrons. So some of the symbols you need to know are that single, double, and triple bonds are represented as dashes. A single bond is 1 dash, double bonds are 2 dashes, and triple bonds are 3 dashes. For ionic structures, you only have one reasonable structure, as you're donating or accepting electrons. And so, as in this NaCl structure, you have a total of 8 valence electrons, as calculated, as seen from the periodic table. 8 divided by 2 gives you 4. Since chlorine has 7 valence electrons, though it's more likely to accept an electron, fulfilling its octet, and since Na has 1 valence electron, it's more likely to donate that, and so you have this structure Na bonded with Cl with 6 free electrons around this chlorine. For covalent structures, it's rather hard. It's harder than ionic structures because you'll have to consider which structure is more reasonable, because you'll have different options to choose from. And so let's look at one of the simplest structures, water H2O. You have a total of 8 valence electrons you have 1 for hydrogen, and you have 2 hydrogen atoms, so you have 2 plus 6 valence electrons in oxygen, which gives you a total of 8. 8 divided by 2 is also 4 pairs, so you'll have a total of 4 pairs of electrons in this H2O structure. So we start out by drawing the rough skeleton of an H2O, and that would be an O in the center and 2 H's on the sides. Since we know that hydrogen only has 1 valence electron, so it can only have one single pair, one single bond, and no free electrons. And so we can confidently draw one single bond on each side, bonded to the central oxygen atom. And since the 2 single bonds already help eliminate 2 of the pairs, electron pairs, this leaves us with 2 remaining electron pairs. How do we use them up? We draw them as free electron pairs around the oxygen atom, and this coincidentally helps fulfill the octet rule in the center oxygen atom. And let's move on to the next example over here, and that is the carbon dioxide molecule. By using the periodic table, we can find that there are 4 valence electrons on carbon and 6 on oxygen. 6 times 2 plus 4 is 16. Divide that by 2 and gives you the total of 8 pairs. So again, we'll first draw the rough skeleton of CO2, and that's C in the center, carbon in the center, and 2 oxygen as surrounding atoms. So let's first start with single bonds. When carbon and oxygen are bonded through single bonds, if we try to fulfill the octet on all 3 atoms, it will leave us with a total of 10 electron pairs, and that does not fulfill this. That is not equal to 8 pairs, and so we do not choose this structure over here where C is single bonded with 2 O's. Instead, we will favor the structure that's double bonded with 2 oxygens, because in order to fulfill the octet, you will need only 2 free electrons on each oxygen, and you won't need any extra free electrons on the carbon. And the total number of electron pairs adds up to 8. 1, 2, 3, 4, 5, 6, 7, 8. And also each octet rule is fulfilled on both the carbon and the oxygen atom. And that's why this structure, the double bond structure, is more favored than the one over on top of it. And so these are just a few of some of the easier examples of how to draw Lewis structures for molecules. In our unit, we might face some harder structures, but knowing these rules, the law of formal charges and the octet rule, you'll find that it's quite simple to draw Lewis diagrams for different molecules, and it's going to prove to be extremely helpful in your course. Thank you.